Thank you, Evnish. Okay, this is a fairly standard ladder question, but except it's got a string in it, so not too bad, but we just need to consider what happens with that string. So going through the question, it says a uniform ladder of weight W and length 2A. So the fact that it's uniform just means that the weight is acting in the center. And then rests in equilibrium on a smooth horizontal floor and a rough vertical wall. So the floor is smooth and the wall is rough. Okay, so because of that, there's no friction on the floor, but there is friction on the wall, and the friction now is acting up. That's to stop it slipping down the wall. Then we're told the coefficient of friction between the wall and the ladder is mu. The ladder makes an angle theta with the floor where tan theta is 2. So with that, if tan theta is 2, I can draw a triangle to work out what sine theta and cos theta are. So tan theta is opposite of adjacent, so that means the opposite must be 2, the adjacent must be 1. So I can work out sine theta by doing the opposite over the hypotenuse, and hypotenuse in this case is root 5 using Pythagoras. So that's going to be 2 over root 5. And also cos then is 1 over root 5 because it's adjacent over hypotenuse. So that's going to be useful. Carrying on, it says a horizontal light inextensible string is attached to the ladder at the point C where AC is a half A. Okay, so the string's attached to the wall at point D, and you're told that the tension in the string is a quarter W. So how that behaves in this is the tension is basically holding the ladder to the wall. So the tension is acting away from the ladder with a force of a quarter W. So that's kind of stopping it from moving. Okay, by modelling the ladder as a rod, can we find the magnitude of the force on the ladder in terms of W? So what I need to do in this diagram is label up any other forces that are going on. So I've got friction at the wall, but the ladder is pushing against the wall, so there's also a reaction force there. At the floor, there was no friction, but there is a reaction force, and that goes vertically up. Let's call it N for normal reaction force. The only other force then is to consider the weight of the ladder itself, and the weight is W, and because it's uniform, we're told that acts in the center. So what that means is the distance from the end is going to be A if the whole ladder is 2A. Okay, so now we've labelled out all the forces, we can start to look at what we've actually been asked to find, which is the magnitude of the force of the floor on the ladder. That is referring to the reaction force between the ground and the ladder. So it's the force of the floor pushing onto the ladder. So we're going to look at finding that. Now with ladder questions, there's basically two things we do every time, which is resolve forces and take moments. We can resolve forces, and we'll do that very quickly anyway, but it's not actually going to help in this part of the question. We'll do it quickly because we probably need it. So if we resolve vertically, vertical forces are going to be this one, and this one, and this one. So if we resolve up, we can say N plus the frictional force minus the weight force equals 0 because it's all in equilibrium. If we resolve horizontally, the horizontal forces are this one and this one. So that would be a quarter W minus R equals 0. Now what you've got there is two equations with 4 unknowns. We can't solve it like that then. So we are going to have to go and take moments anyway, but we'll be able to decide where's the best place to take moments. The question does say find the force in terms of W, so in fact we could probably eliminate 2 of the forces by taking moments about B, and then all we've got left is N and W, so we don't actually need the resolving parts anyway. So let's take moments about B. And now, considering anything away from B, first force I'm going to hit is W. Now this is the tricky bit. In order to take moments, we need to do force times perpendicular distance, or if it helps, you can do distance times perpendicular force. So I'm going to look at the perpendicular forces. That force there is going to be W times some sine cos, something like that, of theta. This looks very similar to inclined planes questions, so that's actually going to be W cos theta. The distance it is from B is A, so that's its moment. Okay, that's because the angle here is the same as the angle here, so it's just going to be W cos theta. The next force I come across is this one. Now this one's a little bit trickier to spot, so it's probably easier for me to draw that over here. And the angle that I have here is also theta, because those are corresponding angles. So I can call that a quarter W, and this is going to be sine theta, because it's opposite the angle this time. And the distance that is from B is 1.5 A, because there's a half A down here and the whole thing is 2A, so that's going to be 1.5 times A. The last force to consider, which is actually going the other way, is actually going clockwise and the other two are anti-clockwise, is the force at A. So that's going to be N times, and this one is going to be, and again, if you drew that over here, we can see that the angle we've got is theta again. It's going to be cos theta this time. So that's going to be minus, because it's going the opposite direction, N cos theta times 2A. So if the whole thing is in equilibrium, the sum of the moments is 0. So I get that. Whoops, forgot a theta. So if you're confused about where any of these bits have come from, I'm going to do a follow-up video to show you in more detail where these angles come from and everything. But I'll just continue on with this question for now. So what we can do now is look at the values that we've got for sine and cos theta. Now we worked out that cos theta is 1 over root 5, so this is going to be W over root 5A plus a quarter W. Sine theta is 2 over root 5, so it's times 2 over root 5 times 3 over 2A, minus N cos theta again is 1 over root 5 times 2A. And we can simplify all of this. I'm just going to quickly simplify that. WA over root 5 plus, this is going to be 3 over root 5, sorry, 3 over 4 root 5, WA minus 2n over root 5A. Easiest thing to do is probably multiply everything by root 5. Gets rid of all the mess. So we get WA plus 3/4 WA minus 2NA. So 1 plus 3/4 is 7/4, so it's 7/4 WA equals 2NA. A's cancel, and finally we get N is 7W over 8. Okay. Part B says show that mu is greater than or equal to 1/2. So what this is going to be using is the rule for f equals mu r, or f is less than or equal to mu r. I can rearrange that to say mu is greater than or equal to fr over r. So this is where the resolved bits are going to come back in. Okay, so in the previous question we found that n was 7w over 8, and this is going to be useful now. So we're going to look at the two resolved equations, and that's where this comes back in. So if we take the one resolved vertically, n is 7w over 8 plus the frictional force minus the weight force equals 0. And rearranging that will give us friction in terms of w. So we get friction equals w minus 7w over 8. So the friction is w over 8. So that's going to be useful. Now we'll use the second one. Quarter w minus r equals 0 tells us that r equals 1/4 w. That one's easy. Now we just got to put them all together. So knowing that mu is greater than or equal to friction over the reaction force, finally mu is greater than or equal to w over 8 over w over 4. W's cancel, and that becomes 1/8 over 1/4, which is 1/2. So mu is greater than or equal to 1/2. Final part of the question says, state how you've used the modelling assumption that the ladder is a rod. So you need to learn some of these definitions, and a rod is basically some modelling thing that doesn't bend. So if you write down doesn't bend, that will get you the mark. And the point about it not bending means that the forces and all the everything acting on the ladder acts linearly. So we can take perpendicular distances in order to calculate the moments. Also has negligible thickness. Negligible. Oops. This means we can pretty much treat it as a very thin object. So the point of that is that the forces are basically acting on the surface of the rod and not somewhere within it. Okay, that's question 8. I'll do a follow-up question for all the angles and bits like that as well.